This first slide is to just introduce some new notation. We know that R, Q, and Z are the real numbers, the rational numbers, and the integers. If you see a star in the upper right-hand corner, like here, that means the non-zero reals. We've just taken 0 out. And likewise, if you see a plus in the upper right-hand corner, that means that we are only considering the set of positive numbers, not 0 and not the negatives. The first definition is that of a binary operation. Let S be a non-empty set. A binary operation delta on S is a rule that assigns to every ordered pair AB in S cross S a unique element of S, denoted A delta B. So what this is saying is that delta is a mapping from the Cartesian product S cross S to S. That's really all we need to say, is that it's a mapping, it's a function. It picks up every ordered pair in the Cartesian product, any ordered pair in S cross S, and maps it to one and only one element in S. Now, you're not used to thinking of binary operations this way, but an example would be if delta is addition, and we are talking about adding in this set of integers. Then, you don't have to think of it this way, but we just talked about functions, so why not see that this is really exactly what it's saying. Addition is a binary operation that assigns to each element in the cross product a unique integer. For example, it would send the ordered pair 2, 7 to the number 9. Addition is a binary operation on Z. The fact that it produces only one element of the set, another way to say this is that the operation delta is well defined. Can't get two different things. The rule will only produce one. And another word for saying that it produces a unique element of S, in other words, it always gives you an element of S, this is called closure. S is closed under the operation. Here is a general definition of what closure means. If delta is a binary operation on a set S, and H is a subset of S, then if AB in H always gives you A delta B in H, we say that H is closed under the operation. So let me give you an example. Let's say that we've got this set of integers here, and they are broken into two subsets, the evens and the odds. So E and O are both subsets of Z. One of them is closed under the operation of addition, and one of them is not. So we're considering Z under the operation of addition, Z together with the binary operation plus. E, well, if you add two even numbers, you get an even number. So we say that E is closed under addition. O, however, is another subset of Z, and O is not closed. And you can show that it's not closed by just by giving one example. Taking like 3 plus 7 is equal to 10, which is not an O. If you wanted to prove that E is closed, then you have to do it in general, because you're saying every element in there that the set is closed under addition, regardless of what two you pick. So one example doesn't do anything for you. But you could say, well, let M and N be in E. Then M is equal to 2 times A for some integer A. and n is equal to 2 times b for some integer b. So m plus n is equal to 2a plus 2b, which is 2 times a plus b. In other words, m plus n is 2 times a number, which means m plus m is in E. So this would be a proof that E is closed. You have to prove in general. If you want to show something is not true, one example would be just fine. You've seen these properties many times, probably since before high school. If for all A, B, and C in S, we have this. Whoops. We have this holding true. In other words, if you delta B and C first and then A, it's the same thing as A delta B first and then delta C. That means that the operation is associative. And if A delta B is equal to B delta A, we say that the operation is commutative. Examples of operations on sets that are associative and commutative would be addition and multiplication on the sets R, Q, or Z. So we know that addition and multiplication on, well, let's just put R. Addition and multiplication are both associative and commutative. But what about subtraction? Two operations we know are commutative and associative are multiplication and addition on the real numbers, the rational numbers, and the integers. You've known that for years. What about subtraction? Is subtraction associative? Well, no, it is not, and it is not commutative. To show that it's not associative, all you need is an example. Subtraction is not associative. And just an example will do. 1 minus 2, 2 minus 3 is not equal to 1 minus 2 minus 3. That does it. Subtraction is not commutative. Now remember, I know you know this, but the question here is, how do you prove it? If you want to prove that something is not true, it's enough just to say, well, 2 minus 3 is not equal to 3 minus 2. And that's it. Now we have the definition of an identity element. Let delta be a binary operation on S. E in S is an identity element for delta if A delta E equals E delta A equals A. In other words, if you operate with E on either side of any element, you just get the element back again. The identity element commutes with every element in the set, and it always gives back that element. An example, well, you know that 1 is the multiplicative identity. In, we could say in R, Q, or Z. I'll just say R. And 0 is the additive identity. I'll put R, but it's R, Q, or Z under the operation plus. Now this is a problem like you will work on in class. We want to prove that if there is a binary operation on a set S and there is an identity, that it is unique. There are not two of them. So there's always a way to prove uniqueness. So you should add what's written in red off to the left there to your list of how to prove things. To prove something is unique, you suppose that there's more than one. Well, then there'd have to be two. So you suppose there are two and show that they must be equal. And then you have shown uniqueness. So in this example, we will do just that. We have a set S with a binary operation, and we will suppose E and E prime are identity elements in S for delta. Well, what does that mean? Now remember, you're going to look at what I write down right now and you're going to think, well, how did she think of that? Well, I probably wrote down a bunch of other stuff first. You just start writing down what you know. Look at this. E delta E prime is equal to E because E prime is an identity. And E delta E prime is equal to E prime because E is an identity. But delta is a binary operation. So E delta E prime only gives you one answer. And we can conclude, so E is equal to E prime. And thus, the identity is unique. Here we define inverse elements. Let delta be a binary operation on S with identity E. And let A be some element of S. If there is a B in S with the property that A delta B equals B delta A equals E, they commute, both ways give you E, then B is called an inverse of A, a delta inverse of A. Here are some examples. If we take the real numbers under multiplication, we have our identity, of course, E is equal to 1, the multiplicative identity, and all of the non-zero reals have inverses. Notice non-zero. For example, I could say 2 inverse is equal to 1/2. This is the notation that we use. A inverse is the inverse of A. It does not always mean 1 over, but in the real numbers it does. In Z we have a multiplicative identity, it's 1. Now here in Z, 2 does not have an inverse, but 1 and minus 1 do. So I could say the inverse of minus 1 inverse is equal to minus 1, because when you multiply them together, minus 1 times minus 1 gives you the identity. Now in the integers, only 1 and minus 1 have inverses. In the reals, under multiplication, everything but 0 does. But notice down here, here we have the 2 by 2 matrices with real entries under multiplication. Multiplication is definitely a binary operation on that set. You can take any 2 matrices, multiply them, and get 1. So it is a binary operation. Now, of course, not all 2 by 2 matrices have inverses, but if the determinant of A is not 0, we call the inverse A inverse exists, right? So notice you use the same notation. It does not mean 1 over A, does it? 1 over a matrix makes no sense. This is the way we read it, A inverse. Now, for sets, we always use this notation, A inverse, this. But if the operation is addition, that's the only time we don't use it. If the operation is addition, we denote A inverse by minus A. So if you were looking at this set of matrices under addition, the additive inverse would be minus capital A. Now I'd like to prove for you that inverses are unique. So now I would like to prove that if an element has an inverse, that inverse is unique. And unfortunately, I didn't think of it when I recorded this, or when I wrote the outline. The operation does have to be associative. So we will prove that if delta is an associative binary operation, that the inverse is unique. So the first thing we have to do, according to the tip that I gave you on the last couple slides, to prove uniqueness, we have to suppose that there isn't some element that has more than one. So let's suppose there is an element A in S that has more than one inverse. Well, let's say B and B prime are inverses of A. Well, then, let's just write down what that means. A delta B is equal to B delta A is equal to E, and A delta B prime is equal to B prime delta A is equal to E. So we know those two things, and we're thinking I want to get B equal to B prime. So after a little thought, I'm going to write A delta B prime is equal to A delta B, which is equal to E. Now I'm going to multiply on the right by B. I get B delta A delta B prime equals B delta A delta B. But now we said that this was an associative operation, so I can say that B delta A delta B prime is equal to B delta A delta B. There's other ways you could do this. But now B delta A is E, so that's E delta B prime is equal to B delta, and again, A delta B is E. And we get, therefore, this implies that B prime is equal to B. Sorry, I put this in the wrong order. I should have had it after we define what a group is, but just stick in the word associative binary operation. You see where I had to use it was right here. I had to use associativity to get this. So in another 2 slides, all of our operations will be associative, so it's okay. So now I'd like to just go through some very simple sets with operations and ask ourselves if they are binary operations, and if so, are they associative, commutative, is there an identity, and what elements have inverses. Plus is a binary operation. Plus is a binary operation. Plus is associative. We know all this. Plus is commutative on Z. And there certainly is an identity. 0 is the plus identity. And everybody has an inverse. So all integers A have inverse minus A. If we look at Z under the operation subtraction, however, It's not as nice as with addition. Certainly, subtraction is a binary operation. But it is not associative, and it is not commutative. And I think we've already discussed that. It's not associative. It's not commutative. And you can just show by example that those properties do not hold. And there is no identity. No identity. It's true that A minus 0 is equal to A, but it doesn't commute. But 0 minus A is not equal to A, so it's not an identity. The identity has to be a right-sided and a left-sided identity. And if there's no identity, we don't even ask about inverses. Now, the set E of even integers is a subset of Z. Is E closed under subtraction? And the answer would be yes. Because if you take two even numbers and subtract, you get another even number. Are the odds closed under subtraction? No. For example, 3 minus 7 would be negative 4, which is not in the odds. This is a little bit trickier one. We're going to define that symbol to be the exponentiation operation on the positive or the non-negative integers. That is, for all non-negative integers a and b, define a caret b to be a to the b power. And we'll assume that 0 to the a is 0, and that 0 to the 0, we'll just define it to be 1 for now. Okay, so certainly it's a binary operation. You don't get two different things. And you can raise any integer to another integral power. So let's see if it's associative. We want to ask ourselves, is a caret b caret c equal to a caret b caret c? This is like what you have to do in class. So let's see, is it associative? Well, a caret b here, we know that's a to the b caret c, and this is a caret b to the c. So this on the left would be a to the b raised to the c power. And on the right, we would have a raised to the b to the c power. And this is not true. It's certainly not commutative, and there is no identity. So this, although it was a binary operation, it has none of our special properties. Here's one you're familiar with. We have the 2 by 2 matrices with real number entries under the operation of addition. Well, certainly you can add any two matrices and get another one, so we know that it is a binary operation. Yes, it is associative. And by the way, you can always use the fact that matrix multiplication and matrix addition is associative. You don't have to prove that. We do have an additive identity. 0, 0, 0, 0. The 0 matrix is the identity, and we call it capital I. And given A equals A, B, C, D, given a 2 by 2 matrix, we know that it has an additive inverse, which has just the entries minus A minus B minus C minus D. So every inverse has a matrix. This has all of the special properties. Well, what about that same set of 2 by 2 matrices with real entries under multiplication? Again, it's a binary operation. It's associative and not commutative. I assume that you know those things. Matrix multiplication is not commutative. It does have an identity. The identity is one we're all familiar with. 1, 0, 0, 1, a multiplicative identity. But now not all matrices, 2 by 2 matrices, have inverses. Only singular matrices. Only if the determinant of A is not equal to 0. Only if the determinant of A is not equal to 0 does A have an inverse. And we denote that inverse as A inverse. For example, a matrix like 1, 1, 2, 2 has no inverse. And the last thing I wanted to do was finally define a group. This is the most basic algebraic structure that we study. Let G be a set together with the binary operation delta. G is a group if it has the following three properties. Delta is associative, there is an identity, and every G in G has an inverse. So that needs to be memorized, and you can look back on the sets that we've talked about today and see that just a few of them were groups. I'll write down the ones that were, and you can go back and verify. The integers were a group under the operation of addition. The 2 by 2 matrices with real coefficients were a group under addition, matrix addition. And although we didn't prove it, we'll do it in class, GL2R, the set of invertible matrices, is a group under multiplication. And I think those were the only three that were really groups that we looked at.